readies.
All right. So I really focus on the biochemistry and molecular structure of telomerase. As a chemist, I prefer to work at the molecular level. So usually the first thing I do is strip all that cell stuff away such that I can work with the purified enzyme. So here, these are immortal cells we've grown in culture, but these are kind of special. So using the techniques of genetics and molecular biology, we've essentially reprogrammed these cells to produce 300, maybe 400-fold more telomerase than nature usually gives us. And that allows me to get sufficient quantities of telomerase to do biochemistry and explore molecular structure, so three-dimensional shape. So really, the first thing I do is I take.
So what are you doing? You're extracting telomerase?
Yeah. So essentially, the first thing I'm going to do is extract the telomerase from the cells. So this is what we call a lysis buffer. It has salts like potassium and has detergent and buffer and so on. And that's going to essentially dissolve all of the cellular bits. And so we go from a pellet to essentially a solution with all the different components of the cell, okay? And that includes telomerase. So that we leave on ice for a little while. Now, one of the key materials I use to extract telomerase from here is called an antibody. We've engineered an antibody to recognize telomerase. And here, so I recently purified some of this antibody. And so we can analyze proteins, antibodies in different ways. So these bands represent the antibody which we purified. And just with a handy little razor blade, what I'm going to do, I'm going to just cut out one of these bands. I'm going to just plop it in this tube. And this I'll take up to the mass spectrometers upstairs in Procan, and they're going to analyze it for me, just as they do many other proteins. What?
You're going to walk towards me and walk out, is that it?
I wasn't going to do that just yet, but
That's okay.
yeah.
Okay, what are we going to do next?
Oh.
That's all good, so far.
Yeah, I was just, again, just give a brief overview of telomerase and my goals. Yeah, so telomerase, it's found in about 90% of all human cancers, representing essentially every different cancer type, every different tissue type, and cancer cells rely on telomerase for their uncontrolled growth. So if we can develop a therapeutic, like a small molecule that will block the action of telomerase, then that should stop or at least control the growth of cancer cells. And so telomerase as a molecular target really has this broad scope about it. And to develop molecules that will inhibit telomerase, before you can do that, you need a really good grounding in the enzyme, enzymology, and a little verbal diarrhea going on here.
No, stay with me. Go back to this.
Huh?
That's good.
Yeah.
And I'll go on a slightly tighter effect.
Right.
And
When you're ready, stop.
Okay. So I focus on the biochemistry and molecular structure of telomerase. As a chemist, the first thing I do is sort of strip that self stuff away.
oh, sorry, the camera's doing very weird things, going in and out of focus. I was crazy.
Huh.
Scott, if you're ready.
So I focus on the biochemistry and molecular structure of telomerase. So as a chemist, so the first thing I do is strip all that cell stuff away, so I can purify the pure molecule on its own. I tend to work at the molecular level. So here, what I have, these are immortal cells we've grown in culture. They have telomerase, as most immortal cells do, but these are a bit special. Using the tools of genetics and molecular biology, we've reprogrammed these cells to produce about 400-fold more telomerase than nature gives us. And that allows me to get sufficient quantities of telomerase to do very detailed biochemistry and three-dimensional molecular structures, or molecular imaging. One of the first things we do then is we take the cells and we suspend them in what we call a lysis buffer. So it has salts like potassium and sodium. It has detergents. What that does, all the cellular components end up as a solution, and then that's the first step in which I can then extract telomerase from the sample and obtain it in high purity. Now, telomerase is present in about 90% of all cancers, representing essentially every different tissue type and organ. So as a molecular target, it has remarkable scope. Now, cancer cells depend on telomerase for their uncontrolled growth. Then the idea from a therapeutic perspective, if we can develop, say, a small molecule that blocks the action of telomerase, so a telomerase inhibitor, then that will hopefully control or even stop the growth of the cancers. The idea has been around for about 3 decades now, but science is pretty slow. Telomerase is a pretty tough enzyme. Well, about 10 years ago, actually, the biochemistry was a sufficiently advanced stage that I could actually properly pursue identifying a telomerase inhibitor, and it worked. I do have a small molecule telomerase inhibitor, which I use in the lab. It works, as we say, in a test tube. So it's a great research tool. We can address very interesting questions in cancer cell biology. It's sort of at a transition point where we'd like to convert this research tool into something that can be safely put into a human. Okay? And that transition is broadly called, that's drug development. And we're kind of at that transition phase. A key goal to enable that transition is molecular structure. Okay, so what does the enzyme look like? And more specifically, molecular structure with the small molecule inhibitor bound inside telomerase. Okay, that's going to tell me exactly where the inhibitor is binding in telomerase, how its mechanism of inhibition, and crucially, it's going to tell me how I can modify the inhibitor to make it more potent, more specific, and a safer compound to put into a human.
What's a more common name for inhibitor? It stops it, does it?
It stops it. I wouldn't call it a therapeutic yet. It's not therapeutic.
So when you say it's an inhibitor, you're basically saying, well, it slows the growth or it stops the growth, or
So it blocks the action of telomerase.
from doing that?
The inhibitor blocks the action of telomerase from lengthening the telomeres of the cancer cells.
Try that again in one run. Try that again in one run.
Yeah. Let me back up. So telomerase is present in about 90% of all human cancers, representing every different organ and tissue type. It really has a remarkably broad scope across the cancer spectrum. Telomerase, its function as an enzyme, it lengthens the telomeres of cancer cells. Telomere lengthening enables the cancer cells to grow without limit. then from a therapeutic perspective, the idea is then if we can develop a compound that blocks the action of telomerase, prevents it from lengthening the telomeres, then the cancer cells will eventually stop growing and hopefully die. That's the general idea with respect to telomerase in cancer. It's been around for 3 decades now. Telomerase, it's a pretty tricky enzyme. About 10 years ago, the biochemical methods I've established put me in a position where I can really systematically explore identifying a small molecule telomerase inhibitor is the term we use. An inhibitor, the compound that will block the action of telomerase. And that endeavor was successful. I do have a small molecule that completely blocks the action of telomerase, so prevents telomere lengthening. It's kind of at the point where we call it it's a great research tool. It works great at the lab bench, and we can address questions in cancer cell biology. It's kind of at a transition phase.
We cut there, so we lost the line.
So about 10 years ago, the biochemistry of telomerase, it was established well enough that I could then seriously explore, identifying a molecule that would block the action of telomerase, so prevent telomerase from lengthening the telomeres. No telomere lengthening in the cancer cells, then the cancer cells will eventually stop growing and hopefully die. And that endeavor was successful. I did identify a molecule that absolutely 100% blocks the action of telomerase, totally prevents telomere lengthening. It's at the point where we would describe it as a great research tool. It works great in the laboratory bench. We can address questions in cancer cell biology. The challenge now is transitioning from a research tool to a compound that we can safely put into a human as a new therapy. And one research endeavor essential to this is molecular structure, so molecular imaging. We'd like an image of telomerase with the inhibitor. I didn't say inhibitor yet, did I?
No, it's the first time, but now you stopped it, but we can go back.
Yeah.
But it's good. What you're saying is really good. It works, right?
Yeah, I think so. Anyway, so that endeavor was successful. I didn't identify a molecule that, absolutely 100% blocks the action of telomerase, completely prevents telomere lengthening. We call it a telomerase inhibitor. This molecule, it's at the point where we describe it as a great research tool. It works in the test tube at the laboratory bench. We can address questions in cancer cell biology. Now the challenge then is to go from a research tool, transform this molecule into something we can safely put in a human. And one research activity that's essential to this transition is molecular structure, so 3-dimensional molecular imaging. We'd like an image of telomerase with the molecule bound inside. That's going to tell us how this molecule is working and reveal ways that we can change the molecule to improve its potency and its safety and transform it into a new therapeutic.
And your wildest dreams, once you've got it so you can inject into the human body, what would your perfect expectations be?
Given the remarkably broad scope of telomerase across the cancer spectrum as a molecular target, the potential of a good telomerase inhibitor, to transform cancer treatment is, it's quite profound. It could potentially be applicable to almost all cancers of any different tissue type and so on.
And that wouldn't be stopping them, it would be slowing them.
It would
or ideally?
You answer it in a more emotional way, like Stuart just
Yeah,
said to you,
yeah.
you know, in your wildest dreams.
Right.
Come on, you've
Yep,
laid awake at night in bed thinking
yeah,
about
yeah, I
it. Come
know.
on. If
No.
everything goes well,
And okay, all right.
Not getting any younger. What's the dream? What's the legacy?
Yeah, right.
step in.
Yeah, yeah,
Don't
yeah.
be afraid of this. Don't
Yeah,
let
yeah,
People, we won't put it in if people. You know,
yeah. All right. Given the remarkably broad scope of telomerase across the cancer spectrum, such a molecule, a telomerase inhibitor, could really have profound impact in cancer treatment. I mean, it can literally change the way we think about treating cancer. A single compound, safe, that would, control essentially every kind of cancer.
control.
Kill. Okay. Yeah. Okay.
Control's good,
Control is good.
You want
I like
control
kill
or
as well.
stop or
but it's
kill?
not killing, is it? It's not killing.
Well, no. It's
Controlling it.
you want kill or kill is maybe.
Okay.
You're still speaking, I know as a chemist, I know you are a chemist, but can you say something about impact? You know, what do you want to see the impact of your work?
Okay. Yeah. Yeah.
Like if someone said to you when
Yeah.
you were, 90, what was the impact of your work? What would
Yeah,
you
yeah.
love to say? Like, oh, I was part of
Okay. All right.
steps
Yeah.
that led to children being
Yeah.
able
Yeah.
to.
Okay.
Fucking enzymes.
It's fucking inside. Yeah.
I mean, go back to, I don't know what you told Stuart before about, your motivation walking through the kids' hospital, but if you can go back to that motivation. And
Yeah. Yeah.
That's the hope, isn't it? That's the,
Right.
Why
Yeah.
are you here?
Yeah.
What are you doing here?
Yeah.
You can
Right.
trust us.
Yeah. I'm just
maybe
thinking about
Stuart
it.
can ask you a question about what you
Well, once again, look, I really it comes back to and just sort of say it from your wildest dreams when you started
Yeah.
this, when you first discovered it. You go, this
Yeah.
is going to be interesting, and gee whiz, if it all clicks into place, where does it end up?
Telomerase, it has such it's such a broad spectrum. Sorry, that's not what I want to say. It's telomerase. It's just so important across the whole cancer spectrum. Including many pediatric cancers. I walking through the kids' hospital every day, I'm just kind of reminded. And yeah, it would be amazing, maybe a few years, 5 years from now, this molecule I have, or maybe a more future relative of this molecule, will be going into patients, maybe be going into children. I think it has the potential to really transform, how we treat cancer. Think about it. I need a drink.
Yeah, have a drink, have a break.
All right. Maybe I'll back up a little bit to,
Oh, sure. Whatever.
like, okay, I have a research tool. I need to transform it, and how far
I
can it
just
go?
remember in the interview when your eyes widened and you were so excited when you woke up and said, "Fucking shit! What about that?"
Right. Yeah.
And
Yeah.
That feeling, then you couldn't wait to get to
Yeah.
it and see that. And then you can't tell me you weren't thinking what the implications of that would be.
That's long. Yeah. Guess that's a long time ago. Yeah. Okay. Right. So. Yeah. Well, I've been working on telomerase at CMRI now for 22 years. Definitely the longest I've worked on anything. This telomerase inhibitor was 10 years ago now when I first discovered that. So it's been a long haul, but I think it has the potential to really transform how we treat cancer. And I walk through the kids' hospital to and from work each day, so I'm kind of always reminded of that. Telomerase, it's in almost every cancer. including pediatric cancers. So the ability to block it, you know, it potentially could be, you know, just really a mainstay in cancer treatment, and change the way we think about cancer and how we treat it. Yeah.
Well, and then what was the crash?
Steve, was it you?
No, that was me. That was me. No, I bumped this. I bumped this.
Okay, yep.
Okay.
And, all right, good. And you just take, and you're taking it out of there, you're miming taking it out of the old jar. Pretend you're taking the, that thing that you're cutting now out of the Tupperware container.
So this is an antibody.
Don't cut it though. Just
Oh.
mime cutting it. Yep, we'll save that for close. Okay, good. And continue. I'm just up on your face, you say. Okay, and action. I'll move that. That's good. Okay.
All right. I actually need to change that.
Genius. That's now ready for.
But I keep my mouth shut, basically.
Yeah, I think we can just do the.
Okay. All right. Yep.
Here we go. And aren't you going to do the immortal cells first? Don't you pick that cell out and
Oh.
shake it and do all the work?
Okay. We can do that. Let me just.
Is there a cover on top of that?
There is. There is. Yep. Okay.
So we're going to do all that stuff. We're going to lift it up and shake it and do
Uh huh. Yep.
all that.
All right.
Test tube out.
Okay. Doke. Yep.
Okay, and
Yep.
set. Oh, that's good. No, just pick it up into there and shake it again. Just hold it down again and just repeat that action and action.
All right. I'm gonna scooch over here.
And just put that back in and put it back on the flask plate again. Put the jellyfish back in the solution and do that again. And Sorry, can you just take that out and then
Do that again?
Ice again. Wait for it and wait for it and wait for it and wait for it and action. Okay, can you just do it so I can't quite see it?
Oh,
there? I'm
because
just
there's
gonna
behind.
just go here.
Yeah. Right.
Oh, no, that was too much. You can't do it.
Oh, okay.
That's crazy.
So you,
No,
you want everything in the.
oh, yeah. Okay, that's good.
Okay.
And when you're ready, action.
All right. Yeah. Okay. Yep.
Perfect.
Yep.
And action. And rolling up. Just take a step to your left. Yeah, we'll cut there. I'll back up. And camera set. No, you look at me then.
What?
Now look at the camera. Look at
Okay.
like that.
Okay.
And
Yep.
set.
Thumbs up.
Roll up. Andrew, you good? Rolling. And thank you. Rolling. And action. No, hang on, sorry. And
Hey.
okay, let's look good. It's good pre-frame. Thank you. And going back and action. We'll do one more. Cut that. We'll do and action. Okay, very good. And action. Just go way across a bit. Like that. Okay, and okay, roll up.
And rolling.
And action. Action. Cut that.